Hey everybody, welcome back to this course. In this video, I just want to go over the activity for week 3. So this week we're going to be working with signals, device interfacing, and um, programming fundamentals. And so here we are at the most recent release of the lab manual. And we go down to contents and we click on week 3. So here are some of the definitions that you should read over and try to understand. These definitions in particular are dealing with signals and some basic filtering theory. And then the next few, from datasheet down to button, this is hardware specific, and from algorithm down to hexadecimal, is more software definition, or like programming fundamentals, I guess. Right, so this would be devices, and this is programming. Sorry. So I'll let you guys read over those and then reach out if you have any questions. And then here's more in the background. So we're going to be working with the frequency selective filter. And if you recall last week, we fed a function generator, right? When we were able to set the frequency of our output signal going into that function or coming out of the function generator. And so what a frequency selective filter does is it looks at specific frequencies and it kind of rejects frequencies that aren't in some kind of range, right? So if I have a low pass filter, well, this is a filter that will reject will reject higher frequencies and it only lets low frequencies pass through. So it has some cutoff frequency, right? So say we have a low pass filter cutoff at 150 hertz, and if we put in a 200 hertz input signal, well, at 200 hertz, like say it's just a sine wave, so that's not going to pass through our filter. And then on the output, it's just going to be somewhere around 0 volts coming out. So we'll get to play with that idea today and try it out in the lab, right? So we're going to hook up just an resistor in series with a capacitor and kind of just look at the output on the oscilloscope on 2 different channels. So digital filter now, this operates on a sampled signal. Right, so say I've got some sinusoidal tone. Right, so we have a sine wave with a frequency of 100 hertz. Right, so in one period of our sine wave, that's 1 divided by 100 in time. That's voltage, right? So 1 divided by 100. So the idea behind sampling a signal is we measure the signal at some point to reconstruct a new signal, right? So we take a sample at time equals 0, time equals a quarter period, time equals a half period, 3/4 period, and 1 period. So then we are able to construct this new red signal that looks like this, that is now sampled. And what usually happens is we use some kind of approximation algorithm to determine what this signal actually looks like based on our samples, right? So we can use this would be kind of like a linear interpolation, what it's called. And so we just connect the dots in a straight line. You can also have second order approximation, kind of like that. But yeah, so that's the basic idea behind a sampled signal. So a digital filter will need to use a sampled signal as its input. And we're not going to be doing this with the lab equipment, but we'll play around with digital filters in MATLAB, specifically an audio filter and a spatial filter, right? So just looking at images. So here's some little blurb on MATLAB. I'll put up some instructions on how to install MATLAB on your own machine if you're interested. And pretty much it's going to be a really important tool going forward in your career. Pretty much every industry uses it. And the company that I work at actually just purchased the MATLAB license in order to do some stuff. So we're going to be using the signal processing toolbox and the image processing toolbox. These are both provided within our educational license of MATLAB, so that's good. And then we have software flowcharts. So we just use a software flowchart to visualize an algorithm. So we've got terminal points, start and end, and arrows, and a rectangular entry as a process, diamond entry as a decision. Then you have exit points coming out of that decision. So if we look closely here, right, so we've got our start. This is a process. This is something that we're doing. Another thing, and then we go on to the next process. And then down here from eat, we go down to some decision. We check if it's checking if it's a weekend. And then if it is a weekend, we do nothing. If it's not, then we do work. Right, so pretty basic idea. There are a lot of different tools that you can use to create a flowchart, right? Or you could just draw it. I use this draw.io. It's just a website that can link directly to Google Drive, which is nice. And then schematics, right? So if we wanted to draw like a schematic of one of our previous activities, right? So we have our Arduino, let's just call it Mega. And we've got like a resistor into an LED. And then down to ground. So here's the ground of Arduino, and here's pin 3, digital pin. So this is kind of a pretty good example of a schematic. Easy EDA provides a really nice set of tools that we can build schematics and also build a printed circuit board, which we'll be trying to do later in the course. So I recommend using this Easy EDA. You'll have to install it or use a web version. The installation it's definitely been easier to mess around with on my end, but you're welcome to do either one or not. None at all. You can just draw the schematics too. That's fine. So here's the assignment, right? There's the idea of the frequency dependent filter, or frequency selective filter rather. So we're putting in a 1 volt sine wave, and then we're going to mess around with the frequency and calculate the cutoff frequency. So I gave a formula in the background reading on how to calculate the cutoff frequency. And then you're just going to try to make observations on what happens exactly when we approach that cutoff frequency, or when we go over it, I guess. So in the second step, we're loading an audio signal. I'll walk you through that shortly after we go through all of this. So we're loading this audio signal. We're going to listen to it and plot it in the time domain. And then we're going to use a built-in, or like a low pass filter function that's built into the signal processing toolbox, and mess around with the different pass bands. We're going to plot and listen to each output and just describe what happens when we change the passband frequency to our audio signal. Here, again, we're using MATLAB. Instead of an audio signal, we're going to be looking at the spatial signal, which is a picture in this case. So we're going to show a graphic of Kobe. So it's going to be, we just read the image Kobe.png. Then we're going to scale it by, so we're going to store Kobe into a variable and scale them by 1 divided by 4 and scale them by 2, and just kind of observe what happens. This is kind of like instead of a frequency selective filter, this is more of a spatial filter. And actually it's more of a linear process than really filtering anything, but we'll get in, you'll get into that as you progress through your career. So in this last couple parts, these will be done with the Arduino again, instead of MATLAB, right? So these two are MATLAB, and this one is the test equipment in lab. So as you can see, just looking at comparing last week from this to this week, we're building a lot of tools, and we're going to be practicing using all these tools in every single experiment. So if you ever get lost, reach out, ask your friends, and just try to keep up with the material if you can. If you can't, I'll try to scale back the assignments as necessary. So going on to base functionality, we're just pretty much just making a driver for, or I guess we will already have had made a driver for the 7-segment display. And then we're just making like a little program to count. So like we're displaying a count every second. So it's like 0, 1, but then say you get a button press. So then you go 0, 1, all the way up to 10, to 9. And let's say you already registered another button press, 0, 1, all the way up to 9, and then A to F for our hexadecimal count. This is binary, decimal, and hex. And just kind of follow these this specification to complete that project. Hopefully it's pretty straightforward. And now with that, we can go ahead and take a look at some MATLAB. Let me share desktop here. All right, so on Canvas, I provided this installation page. You're going to have to go through, right? So MATLAB access and support for everyone at Cal Poly. And then we can go ahead and sign in to get started with your license and downloading the software onto your own machine. And then when you open up MATLAB, once you've installed, doesn't really matter, try to get a more recent version. But up here, there's this button called add-ons, right? And click on get add-ons, and you should be able to locate the signal processing toolbox and the image processing toolbox just by searching here for signal processing. And look that up. And so there's this little flag here that says that I already have it installed, but basically we just click on this and go through the installation process to get to the add-ons. Right, so like I said, for this experiment, we're just using the signal processing and image processing toolboxes.
Got your bagel, Chris?
So once you have that installed, let's just take a look at the MATLAB interface, right? So here I'm in the command window, I can run commands, so like x equals 1, right? And then it shows that x is x, yeah. Here it shows the working directory that we're in. So we're in my desktop E368. Don't worry about that. But once we click inside of our current folder, we can hit new script to open up an editor. And then we could, so comment in MATLAB is a percent symbol, and you can't see that, so let's zoom in. So this is a comment, right? We'll just name this lab3, and then MATLAB files have a .m extension, so we'll file save this as lab3.m into this folder. It won't make that much of a difference. So this is our MATLAB script now. I can just show you. So here in the command line, right, we can practice running some commands before putting it into a script. We were going to use the handle's Messiah audio file. And to do that, you just hit load handle. And then over here on the left, you can see our workspace. So it has the list of variables and their value. If I load handle, you'll notice that we get this new variable y, which is our time domain signal, and the frequency, the sampling frequency fs. So we can go ahead and now put that into our script. and not mat. So then this is going to load handles Messiah into workspace. We have X, Y, which is the time domain signal, and we have FS, which is our sampling frequency. Now, with those two, we can use this sound function to listen to, just the audio sample of Handel's Messiah, and we can then plot the time domain in figure one. So we call figure one to tell MATLAB that we're going to be plotting this into figure one. And then we plot Y, so the first thing that goes in, I believe, is the x-axis. So this is going to be 1 through the length of Y. And it's really neat. MATLAB has this built-in function called length that we can just get the length of a matrix. Everything in MATLAB is kind of stored in a matrix. These scalar values, 1 and 81, 92, is actually just a 1-by-1 matrix. Right, so we plot the x values, and then we plot the y values, which is just y. So then if we run this, I'm going to make that so that we don't listen to it, but I should be able to run this. And assuming I did everything correctly, yeah, so it plots the audio sample that we have just loaded into our workspace. Pretty neat. And then if you have your volume turned up, it'll also play the music out of your speakers. So that's how you get started with the audio portion. MATLAB also has this list of built-in images. I've also linked onto the Canvas page here. A list of MATLAB built-in demo images, and these are from the image processing toolbox. So here's just from the forum. Right, so here's a bunch of the images, and here's what they print out as well. They're all numbered and whatnot. Let's just work with this circles. So circles.png, sure. So we go back into our MATLAB editor, and we can just play around with this on the command window. So in the image processing toolbox, we have a couple functions, imRead. And then in the command window, you have to put a parentheses to look at the input arguments. Right, so it just takes the file name. And since this is built in, we can just put the path directly, or the file directly. So I think it was circles.png. And so you'll see that now that has stored that in answer. Answer is something that overwrites itself over and over again each time you enter a command. So what you actually want to do is store this in read and then the circles.png into a variable, right? So then we can go back and actually have that variable not overwrite itself every time we type a new command. Right, so now we can move that into our script if we want. So I is equal to imRead, what is this, circles.png. And now to show that, we just call this, we can put that into a new figure, right? So let's say we're working in figure 2, and then we can show this I variable that we have. We save that, run it, and then here's our circles. Kind of interesting picture. It's probably used for computer vision applications for those that are interested. All of these image processing toolbox functionalities are targeted towards image computer vision. So there we have our M show. So the nice thing about MATLAB is that if we want to scale a variable, we can just multiply through or divide. And then it'll do an element-wise operation on the object that we're acting on, right? So this I is a 256 by 256 matrix. We can actually double click this on the workspace, and you can actually look at the matrix, right? So it's just some tabulated data. I'm guessing that it's a binary image, right? So at 0 is where the intensity is low, maybe dark, and the ones is where the intensity is high. So maybe this isn't the best image to work with. Let me look for one that's actually colored here. So let's work with this hand, number 49. Hands one.jpg, or maybe if there's a like colored PNG, gantry crane 44. Yeah, let's work with gantry crane. We open up this gantry crane, PNG, and then we run it. And there we have our gantry crane. Right, so like I said, we've got our matrix here. And it's 264 by 400. And you'll notice now that it's by 3. So this ties back into color theory. So each pixel in our image here has some intensity values in red, green, and blue. And with red, green, and blue, right, we can kind of construct most of the color spectrum. So which is why we have this now 3-dimensional matrix of our images. But like I said, the nice thing about MATLAB is that we can just scale down. So let's say we want to make a 1 by 2 figure, I guess, right? So we can put multiple figures into one figure. So this is the amount of rows in the first number here, number of columns, and this is the entry that we're working at. So if we're 1 by 2, the first entry is going to be the leftmost or the top, I think. I think it's going to be the leftmost image. So we show the original image, and then now we can subplot 1, 2, 2 to get that second entry in our 1 by 2 image. And then let's scale this down by, let's say we scale it down by 3. So we just divide by 3, and that will divide all of the intensities of our RGB matrix here by 3. So let's just see what happens there. Yeah, so there we go. As you can see, the intensity has decreased. So the new image appears a little bit darker. So that should be sufficient, I think, to get you started with the MATLAB portion. The test equipment portion and the Arduino portion should hopefully be pretty straightforward. I think maybe I'll quickly go over Easy EDA if I've got it installed here. So yeah, MATLAB has functionality for pretty much any kind of application that you want. You can go into the MATLAB documentation and look up all kinds of different toolboxes. So it looks like I don't actually have Easy EDA installed right now, but on the quiz I provided an example of a schematic that I built using Easy EDA, and if we get to that portion, I'll go ahead and make another video talking through how to get started with Easy EDA. But I guess with that should hopefully be sufficient to get you started with the experiment. I'll see you guys in the next video. Thanks for tuning in.